Hey, welcome to our session on how to describe the shape or figure out the shape of a graph, session 24. There's such a thing called the first derivative test for telling when a function is increasing or decreasing. It's pretty simple. Remember that the derivative is the instantaneous rate of change for f of x. So whenever that derivative is positive, it must mean f of x is increasing. Conversely, if f of x is negative, then the function values must be getting smaller and it's decreasing. If the derivative is 0, remember that's a critical number and f of x is not changing at that moment. Here's a sample problem. Find the interval or intervals where the function is increasing and or decreasing. Let's say we have f of x equals x cubed minus 12x minus 5. Step 1. Find the domain of the function. Since this function is a polynomial, its domain is negative infinity to infinity. Okay, take the first derivative. F prime of x equals 3x squared minus 12. Once I have the first derivative, I set it equal to 0 to find the critical numbers, which turn out to be x equals plus or minus 2. I set up a table below where I'm using the endpoints of the domain and the critical numbers as endpoints of my individual test intervals. So I have negative infinity to negative 2, negative 2 to 2, and 2 to infinity. Notice the endpoints are not included. Okay, I pick some x test values in each intervals. So I have negative 3, 0, and 3, randomly picked values. And then I evaluate f prime of x at each of those test values. So I get 15. That's a positive value, so in that interval the function is increasing. I get negative 2 for the second negative 12 rather for the second interval, so it's decreasing there, and then it goes back to increasing in the last interval because I get 15. Okay? There's also a first derivative test for finding extremas, maximum or minimum. The next 3 slides we're going to talk about what the first derivative tests. Consider the following graph, which is really a graph of y equals x squared. Notice, on the left-hand side of the graph, where an x is negative, I've drawn short little red lines which indicate the tangent lines. Notice that the slope of these tangent lines are negative, okay? And as I move from left to right on the x-axis, the slopes go from negative to 0 at the origin to positively sloped tangent lines, which means the derivative is positive there on the right-hand side. If you look at this, you can see clearly the origin is a minimum value for the function. So let's look and see how the derivative changes as we go around the critical number of 0, 0. Looks to me like the derivative goes from negative to 0 to positive. Okay, so for any case where you have a derivative changing from negative on the left-hand side of a critical number to positive on the right-hand side of a critical number, that critical number is going to be a minimum. The converse would be true for maximum. In other words, if the derivative goes from positive to 0 to negative, then that critical number would be a maximum. Think of a u. A u would be a minimum, and an upside down u would be a maximum. So like I said, if f prime of x changes from negative to positive on either side of a critical number, then that point would be a minimum. If it changes from positive to negative, then that point would be a maximum. This table summarizes this, where C represents the critical number. Sample problem. For f of x equals x squared minus 3 times e of x, find the interval where it is increasing or decreasing, and also local and absolute extrema. Step 1, find the domain, which in this case is negative infinity to infinity. Step 2, take the derivative. Well, we got to use product rule here, and if you see, the derivative simplifies out to e to the x times the quantity x squared plus 2x minus 3. That quantity is factorable, so what I do is I set it equal to 0 and I factor it, and in step 4 I get e to the x equals x plus 3 times x minus 1 equals to 0, and this will happen when either x is negative 3 or 1. Therefore these values would be critical numbers. Then we're going to set up a table which you'll see in the next slide. Okay, I've recopied my original function and my first derivative here, and I have a table set up over the endpoints of the domain and the critical numbers. So I have 3 intervals to test in. I pick these x test values randomly. I pick -4, I pick 0, and I pick 2. Then I evaluate the derivative. I get 5 over e to the 4th, which is definitely a positive number. I get -3, which is a negative number. And I get 5e squared, which is definitely a positive number. Okay, I've also included the function values there. So x equals -3 has to be a maximum because the derivative goes from positive to 0 at the critical number to negative to the right of the critical number. And x equals 1 is an absolute min because it goes from negative to 0 to positive on either side of that critical number. It's an absolute because to the left and the right of the function at that critical number, especially to the right, the function continues to increase. So that I know that it doesn't get any smaller than the function value at 1. And the function value at 1, we haven't evaluated, but the function value at 1 would be -2 times e. So -2e would be the minimum value of the function. Concavity. Let's look at a graph y equals x cubed and do some discussion on this. Okay, I've drawn the graph here, and if you notice on the x-axis from -infinity to 0, it appears to be what we call concave down. Okay, like a U turned upside down, 1/2 of that U turned upside down. And on the right-hand side is what we call concave up. So from -infinity to 0, we would say the graph is concave down, and from 0 to infinity, the graph is concave up. So how do we determine what the concavity is of the graph? Intervals where the second derivative is negative are concave down, and intervals where the second derivative is positive are concave up. Notice that x equals 0, it's neither concave up or down, but changes from concave down to concave up. This point is known as a point of inflection, which is called a point of change. Okay, so now if you look at this graph, look at the left-hand side and imagine the slopes of the tangent line, little line segments as I'm moving from left to right. Those slopes become less and less steep until I get to 0 at the origin, and that would be a horizontal line. So if we think of the second derivative as the rate of change of the first derivative, the slopes of the tangents would be becoming less and less. That means that the first derivative is changing in a negative manner. So our second derivative should be negative. Therefore, that's the test for a concave down would be a negative second derivative. And the converse is true for concave up. Sample problem. Let's look at y equals 3 plus sine of x on the closed interval 0 to 2 pi. First step, they've already given us the domain, so take the first and second derivative. F prime, cosine of x. F double prime, negative sine of x. Step 2, find values that make f double prime of x 0, okay? And those values would occur when x equals 0, pi, or 2 pi. Step 3, let's set up a table of intervals with the endpoints equal to values obtained in step 2. So I have an endpoint of 0 to pi and pi to 2 pi. Then I pick some test values randomly, pi over 2, 3 pi over 2. Evaluate the second derivative. I get -1 and 1 respectively. Conclusion, a negative second derivative tells me the function is concave down. A positive second derivative tells me the function is concave up. So our conclusion would be the graph changes from concave down to concave up at x equals pi. And actually x equals pi would be what we would call a point of inflection. Let's talk a little bit more about points of inflection. They can be found by checking the second derivative for values of x that make it either 0 or undefined. Take values on either side of these x values and evaluate the second derivative at these values. If it changes from positive to negative or negative to positive, then that x value is a point of inflection. If you do not get a sign change on either side of these values, then there is no point of inflection. Find the points of inflection, if any, for the function y equals x to the 1/3. Step 1, find domain. All real numbers. Step 2, take second derivative. First derivative is indicated here. Second derivative, think of that as really as -2 over 9 times x to the 5/3. It's clear that there's no value that will make that equation 0, but there is a value, namely x equals 0, that makes it undefined, because you'd be dividing by 0. So this is the point we want to look at. Set up tables to test values on either side of 0 for a sign change. Okay, here we go. I've got my intervals set up, -infinity to 0, 0 to infinity. My test values chosen at random yield f double prime of 2/9 and f double prime of -2/9 respectively. I have a sign change. Therefore, even though x equals 0 is undefined in the second derivative, the point 0, 0 is in the domain of my original function, and since it's a valid point and there is a sign change, we would describe this as a point of inflection where the curve changes concavity. The last thing we're going to talk about is the second derivative test for extrema. Let's go back to our old friend y equals x squared and its graph below. Notice that it's concave up over the entire domain. This would tell us that the second derivative has to be positive all the time, and any critical numbers that I insert into the second derivative, in this case x equals 0, would yield a positive number when put there. In this case, f double prime of x equals 2, which is always positive. Therefore, x equals 0 is an absolute minimum. If you also look at the curve, and let's see what the first derivative is doing, can you see that the slope of the first derivative, the tangent slopes are negative on the left-hand side of the origin, there's 0 at the origin, and positive on the right-hand side of the origin. Therefore, the rate of change of that first derivative has to be a positive rate of change, which means our second derivative would be positive. So I know I have a minimum when the second derivative test is positive. How do you set up a table? Well, let's pick a function, x cubed minus 12x minus 5. There's the first derivative and the second derivative. There are critical numbers here at x equals 2, -2. Let's test them. F double prime of 2 equals 12, f double prime of -2 equals -12. So therefore in the table, if I get a positive second derivative, it tells me I have a minimum, and if I get a negative second derivative, it tells me I have a maximum. So my conclusion is that 2 is a minimum and x equals -2 is a local max. What I'd like you to do now is pages 273 to 274, numbers 7 through 34. Make sure that you take notes on this video and watch it several times, as there's a lot of information on it and it is all essential. You're going to need this information for the rest of the chapter. Thanks and have a good evening.